this presentation, we will introduce FathomGPT, which is a natural language interface for exploring ocean science data. So the background is that we collaborated with Monterey Bay Research Aquarium Institute for around a year to develop an interface that could interact with the FathomNet database. So this database is an open source ocean creature database that aggregates labeled image data of around 100K creatures in the ocean. And the ocean scientists want to use this to collect and analyze the ocean creature data to monitor changes in the ocean. So the problem with databases like FathomNet is that it's difficult to integrate into scientific workflows due to complex SQL queries that are required for getting the data that they want, and also because it's not very accessible for non-experts because of the domain knowledge required to query the data or understand the data. And currently, LLMs are not very adapted for domain-specific scientific databases, even though it only works for generalized queries. So some challenges that we face to solve this problem include adapting LLMs to be suitable for name resolution and SQL generation for this specific database, and also improving the latency so that the user could use it more easily without losing accuracy. So we created FathomGPT, which is a chat-like interface where the user could interact with the FathomNet database through our system. So one key functionality is that it's able to do natural language querying so that the user could request for data in a conversational language. For example, just typing finding images of Borrelia aurita. And if they don't know the scientific name, we have a functionality called name resolution, which allows the user to find data by the common name or even by a descriptive feature. For example, they can just find orange creatures, and name resolution will get a list of all the scientific names and find the images from the database. And they could even input image to find similar images in the database. So for example, if they want to identify this jellyfish, they could input that into our system, and it would be able to retrieve the images that are similar so that they could find these scientific names. And it's also able to output a graph to help the user visualize the data in the database so that they could understand and analyze it more easily. So let's see our system in action. So let's say the scientist wants to identify just a type of shrimp. They could input an image and ask it to find similar images. So our system would generate the SQL query and get the images. And they see that these two look similar to the ones that they're looking for. So they could further narrow it down by maybe checking the depths of these two species if they know some background information about this. So they could request it to generate a bar chart displaying the depths to compare these two species. So once they input that, it would visualize the data for these two creatures, and they see that one of them is found at a greater depth compared to other. And they can also find additional images of shrimp to see what other options there are for identifying this creature. So now we'll move on to describing the system architecture. So the pipeline starts when the user inputs a natural language query into the front end. It will then pass it to the back end and send it to the prompt evaluator stage. So this is an LLM that understands the natural language prompt to determine which functions to use. For example, if it has a common name or a descriptive feature, it would do name resolution. Or if it's requesting data from the database, it would do the SQL query generator function. So if in that case, for SQL query generator, it would send it to a second LLM, which would then convert the natural language query into a SQL query. And it will also determine if additional subsystems need to be used, for example, visualization or similar image search, and generate the SQL accordingly. So it will later then execute the SQL query to obtain the results to pass to front end. So one key innovation is knowledge graph name resolution. So this is what allows it to query by the descriptive features. So it's able to this works by, in the pre-processing stage, we converted the Wikipedia pages of all the species in the database into knowledge graphs using LLMs. And when the user inputs a prompt, it would then convert that prompt into a knowledge graph using an LLM, and finally do a KG alignment between the two to obtain the scientific names that match the description. So we believe this is the first system that incorporated knowledge graphs to work in the scientific database, and it's an important component to allow users to access data more conveniently in the data. So this is an example of how the knowledge graph is saved in our system for species. So it's saved as a JSON, but you could visualize it as a knowledge graph like this. And this is how KG alignment would work. So for example, if the user wants to find transparent creatures, it would, the prompt would get converted into a knowledge graph that looks like this with a subject, relation, and object. And it would find the object transparent inside the species KG to align it with one of the species. And it's able to see that Aurelia aurita is one species that contains color transparent. And it would then output the scientific name for that. And now Naveen would describe additional technical innovations.
So basically what the query is, and the system sends the control to either the SQL generation part. So the SQL generation part, we want the system to change the prompt to SQL. So the requirement for the SQL generation part is, so it must be optimized to the FathomGPT's output requirements. It should contain all the attributes and all the details that is needed for the UI. The second requirement is it should be adapted to the database specific queries. For example, it should be able to map the entity to correct database tables and columns. The other requirement is it should handle complex queries. For example, in our case, when we had a big requirement for the investors, and the requirement wouldn't be fulfilled even when we do future prompting. So for that, we used OpenAI's finding API. So what OpenAI says is, if you have a lot of requirements, instead of using like future prompting, you can directly go to the finding API, upload your data in their format, and get a fine-tuned model. Although fine-tuning did help, it didn't solve all of our problems. So what we had to do is separate the text to SQL generation model into 3 models. So we have first image search model, that's fine-tuned model. We have visualization model, that is future prompted model, and we have another fine-tuned model for all other type of queries. So once we get a response correct for a single prompt, we want the system to handle conversation. So what the requirement for the system is like, it should be able to understand the context, what the user said before, what the result that they got before, and it should also be able to handle the tokens and use it in an effective way. So the token users part was specifically a problem in our case, because in the earlier version of GPT-3 that we were using, even with like 3 to 4 conversations along with the huge database structure, it would exceed the model's context length, and we couldn't continue the conversation. So to solve that, we came up with a prompt engineering strategy where we do prompt modification. So what we do is the LLM is provided with the prompt evaluator LLM is provided with all the context from the previous conversation. So the model is prompted so that it should be able to modify the current prompt so that it includes all the context from the previous prompt. So for example, if the prompt first was for a bar chart, and in the second prompt, user does want a bar chart, and the modified prompt that the prompt evaluator will give us is as shown in the slide. So once we have this prompt, we don't need to pass all the previous conversation to the SQL generation part. That improves token efficiency. So the key technical enhancement we had to do is the name resolution part. The common name to scientific name was very complicated, so what we had to work through a lot of solutions, and we settled for easy name resolution. Also, in the initial prototypes, what we saw was, although the system is for research, the research scientists didn't want like a system that would take a minute long, so we had to make a lot of changes to handle the queries, and now the time taken is around 7 seconds. Also, during the visualizations, there will be a lot of data, and for the data to move back and forth, it would take a lot of time. Even in those situations, users, the scientific researchers wanted it to be fast, so we had to do the data retrieval and the visualization code generation process in like parallelly. So now let's look at the evaluation part of FathomGPT. FathomGPT is developed in close collaboration with ocean scientists and researchers. So we did a workshop on the system that we created. So we had over 174 scientists, and they provided many real-world queries to the system. You can see the queries in the right, and we saw that our system works well and is able to generate correct and it is able to generate what results the researchers want about 72.1% of the time. This is more of the filtered queries, because there were a lot of repetitive queries, and we wanted a real-world evaluation of the model. We also did some evaluation studies so that we are sure that the system architecture changes, choices that we wanted is good enough. So we did evaluation study for SQL fine-tuning versus future prompted model, and we got an accuracy of 14.7% improvement. We also checked our prompt engineering strategy of modification of the prompt, and we saw that increases the accuracy by 7.3% while being more token efficient by 15.7%. So the key takeaways from the research is large language model from even 6 months ago can be used to make effective tool, and it can be used to generate a system which can help users solve the problem of SQL generation. Also, from the evaluation studies, we can see that the prompt modification technique works, and we can also see from the result that if we have a complex task for LLM and it isn't able to generate good results, then we can separate the tasks into subtasks, like how we did for the SQL generation part. So.
Thank you for listening to our presentation. We have our GitHub repo available, including a live demo if you want to scan the QR code. And if you want to know more details, you can please read our paper, and we're also happy to answer questions in front of our poster.
We have time for a few questions. Maybe then, could you expand a little bit more, like what was your design process behind this system? So it's a kind of learnings we can apply to similar tasks and similar systems.
Initially, we tried several different LLMs, and we decided that this current one is more accurate and it has better latency, so we decided to stay with this. And for the chat interface, we looked at some existing work, and we found that it would be useful to use this style of interface to access the data.
And did you have any problems with hallucinations, like seemingly right answers but not right?
So we actually did have a problem with hallucination when we didn't have the name resolution. So if we just ask the LLM directly, it will actually generate data, scientific names that are not in the database, or it will actually generate ones that are like, it doesn't match the description that the user was looking for. So we found that using the knowledge graph name resolution was able to limit the hallucination by a lot.
I see. Okay. Thank you very much.